делать. Okay. So let us start. So if I will be not clearly seen, please tell me. So let me briefly remind what was last time, very briefly. So last time we considered natural operation, namely so-called Schouten bracket, or just S bracket, on polyvector fields. And we observed how this bracket is related to odd mechanics. So this odd mechanics is odd in both senses. So it's something very non-usual. So it was first thing. Second thing is we discussed the meaning of BV Laplacian. BV Laplacian was nothing like divergence of polyvector field and that's why it depends on the top form. You see, because of this dependence on the top form, it was missed in 50s. Okay? Once again, let me remind that the divergence of the vector field is what we call the IVI. I put this in these marks. Is actually LV of omega divided by omega. So this thing has generalization. And this generalization could be obtained using differential forms, polyvectors, correspondence. So you take polyvector, that is polyvector. You contract this polyvector with the top form, and here we have omega. So here we have relation between polyvector and differential form that depends on omega top. We also discussed that this correspondence is nothing but odd Fourier transform. So when you are doing Fourier transform, you need a measure. That's why it depends on omega. Okay? And in this correspondence, I'll write it here. The RAM differential goes to this nabla V. Okay? Now, interestingly, even without nabla VV, you can do many things if you not just use this bracket, but write. So now I'll erase things. You can write many interesting things just working with this Schouten bracket. In particular, very interesting thing is such equation. And it is called classical master equation. Of Batalin and Wilkowitz. Later, I'll explain why it's called classical, but here I'd like to discuss a bit its geometrical meaning. So, in ordinary mechanics, we have a phase space phi. And if we have Hamiltonian and Poisson structure, we have the bracket. And evolution of observable with time is given by so-called Poisson dynamics. Maybe it's better to write it like this. So this is Poissonian formulation of classical mechanics. So actually, this should be studied in the course of classical mechanics. However, when I was studying at Moscow Physical and Technical Institute, we did not put, so professors did not put enough attention to this. What's interesting is that this is just h to the power of 1 expansion of Schrödinger equation. Is it clear why it is Schrödinger equation to the first order in H?
Yes.
Yes.
Okay, great. So
But can I ask, Shouldn't we change H and F in the bracket? It depends on how we define P, but usually I saw that F and H was in different places. Yes, F was the first and H was the second.
Paul's right.
But it's convention, I would say. I actually think that it's kind of convention. Because, okay, so let us see. It comes from the, so let me try to get the proper sign myself. So we'll write the so-called Heisenberg equation. So it is F sub T. And people do write it in this way. Now let us take derivative. And here we have minus I over H, commutator of H and F. So actually, it depends how you define commutator. You have to put I somewhere. So depending on I, you'll get minus or plus sign. So what is important here is that in classical limit, these two things commute. So 1 over H term drops away. So HF commutator actually starts with H Poissonian bracket plus H squared terms. So when we divide over H, this H goes away, H Planck goes away, and we have this. Okay, but it's not the sign that's important. This dynamics comes from the vector field VH here, when VH is defined by sectional functions. L of VH acting on F is HF. So such vector field preserves the bracket, and people often say that, write it like this, that V is symbolically H with something. And in classical mechanics, you can consider any H. However, here, somehow we have this condition. So we may ask, what is the meaning of this condition? And the meaning of this condition is that since in BV case, where we have polyvectors and not just functions on the cotangent bundle, this bracket is odd. So the vector field is odd. And it's interesting that for odd vector field, you can write down sensible equation, namely that this vector field is homological. LV squared equals to 0. Vector field is homological. And this is equivalent to S equal to 0. So this condition is the condition that vector field that is generated is homological. Okay? So what we are talking about? We are talking about the supermanifold. We can say that, for the example, that it would be T shifted by 1x that contains canonical symplectic form and therefore Poissonic form that is called omega BV, and S such that this S with this symplectic form generates the so-called Q manifold. So Q manifold is nothing but a manifold equipped with this homological vector field. Note that the notion of Q manifold was missed by both French and Russian schools in 50s and 60s and 70s. So French school missed the point that it is a manifold and not just a complex, while Russian school introduced supermanifolds, but they missed this vector field Q, homological vector field. So later on in 90s, I think in 90s, it was Kontsevich and Schwarz who decided that it's better to have this pair, and that this is the proper object. So, in supergeometry, I will draw it and write it in the polite way. In supergeometry, proper thing is supermanifold and Q with condition Q square equal to 0. So Batalyan and Vilkovitsky said, let us add additional structure. And this additional structure is, you may say, omega BV, that is symplectic, or its inverse. This probably should be called PBV. Such that LQ applied to omega equals to 0, or equivalently LQ P equals to 0. So this additional, you may call it mechanical structure. Means that that Q has Hamiltonian. So in mechanics we know that if the vector field preserves symplectic structure, it has Hamiltonian. Such fields in mechanics are called Hamiltonian fields. Similarly, if it preserves Poissonian structure, it also has Hamiltonian. So in this case, we would specify the data. So we have super manifold tilde. It's not that super manifold.
Sorry, but can we ask what does it mean? Lie derivative of pi. Pi is
By vector.
it's tensor field of
Yes.
by vector.
So it's important to know that Lie derivative could be applied to any natural objects.
Okay.
In particular, Lie derivative could be applied not only to functions. Lie derivative could be applied also to vectors.
Yes, I understand how engineers do that, but
No, so I'm explaining the general stuff.
okay.
So general stuff is as follows. So maybe you would like to know how Lie derivative acts on differential form in general. So it's your question.
We know.
In which sense? In which sense? So do you understand how Lie derivative acts on differential forms?
Yes, I understand.
So your problem is to understand how and in which sense Lie derivative is acting on bivectors or
on yes, polyvectors.
So let us do it this way. So maybe you know that. Let us start with vectors. That in vectors we may consider commutator. So this is a Lie bracket. Okay. So this defines an action on vectors, and from this you could guess the formula for polyvectors.
Yes.
But this is still engineer's approach. Let us do something more intelligent. Okay? So, first of all, suppose we have a manifold X and we have Tx. Okay? And actually, we also. So we should also have T star X. Let me see. I'm trying to figure out if the transport. So transport of vector field is natural. Okay. Maybe not this way. Maybe I'd like to do the following. So polyvectors are sections of the tensor bundle to tangent plane. Okay. So say it's kind of it's some pair here, and just suppose. So it is the case for bivector. Suppose we have a diffeomorphism phi. Then diffeomorphism. Naturally goes to the sections of the vector bundle, because it takes vectors here. Okay? Now suppose that this diffeomorphism depends on T, and phi of T is generated by vector field V. in sense that d phi over dt at 0 is v. Okay, so vector field v is tangent to diffeomorphism. Then it acts at all vector fields and also at all polyvector fields. Okay, and this is exactly the Lie derivative. So here we consider the Lie derivative as an infinitesimal diffeomorphism, and everything that could be moved by diffeomorphism is moved by the vector field. And if you want to compute how vector field V moves vector field U, we will get exactly this formula. Okay. At the same time, it is possible to write down explicit formula. And explicit formula in even case. So it was geometry. Now, easy formula. If I have a vector field V and polyvector field pi, then I can say that LV on pi equals to the Schotten bracket. So this is a natural formula. And this is a natural geometric explanation. Okay. By the way, even this Schotten formula in the classical case has a natural interpretation in the case of classical mechanics. Namely, polyvectors are, this way, symmetric polyvector. Okay. So, you see, no, I'm sorry. So it is actually Schotten bracket. However, I cannot interpret it. I'm sorry, I cannot interpret it in terms of classical mechanics. The only way how I interpret it is, of course, classical supermechanics, where you need to see that Schotten bracket is actually odd. Because in this case, it takes vector, vector to vector. So vector has a grading like 1. So it changes the grading. And that is quite interesting. So this thing could be understood only in BV mechanics. So in BV mechanics, polyvectors are functions on T star dot 1x. T star means that they take value on the cotangent vectors. T star 1x has canonical. symplectic form. And also canonical Poissonian form. Given by the pairing between tangent to x and tangent to t star. This form generate Schouten bracket. And that is actually odd. So when Schouten defined his bracket, he was not thinking if it's even or odd, because he was writing formal, just formulas. Now we understand it's odd, because it changes the degree of polyvector. Okay? So degree of polyvector is a number of indices. So in this formula, there is differentiation. Because Schouten bracket actually contains derivative. Okay. And we may consider odd mechanics. So each polyvector could be considered as Hamiltonian. Okay? And then it generates the vector field. So then condition would be that we are interested in such Hamiltonians that generate homological vector fields. So I said the same thing from two sides. Here I started with a Q manifold and asked if this Q manifold actually has Poissonian structure present. And here I started with a very specific manifold with symplectic structure, and I asked if it has a Hamiltonian that generates homological vector field. So it's the same. And here I took very particular manifold, namely T star of 1. And here I am not saying that it's T star of x. I could pick up any symplectic form. Okay? But I just wanted to be symplectic. It means that it is closed. And also, I want it to be preserved by the homological vector Q. Okay, so you may write it down yourself. So it's the best way to understand it. Okay, but all this was the classical story. Because it was classical mechanics. And then Batarin and Vilkavisky said, look, now let us try to write a quantum story for which this classical story would be just a result of classical limit. And so they said, let us come to basics. And do the following. So it's hard to know how they guessed it, basically by analogy between classical mechanics and the odd mechanics. As I said, let us consider such an expression. So this S is a function, and this S of H is a polyvector taking values in formal series in H bar. So actually they were trying to play Hamilton-Jacobi game, okay? So that's what they do. So in what I'll explain, these are polyvectors. However, you can also consider supermanifold with odd symplectic structure. Or more general, consider supermanifold with odd symplectic structure, omega BB. Now, they said the following. Let us write down the master equation. Now let's have a look on what do we have here.
Sorry, can I ask?
Yeah, sure. You're very welcome to ask questions.
I didn't understand what S from H means. It is. I thought that it is like action in mechanics, but
yes, it is like action in mechanics. However, you see that it contains H.
Yes, but why it is polyvector taking values in formal series?
One second. So this S of H is a generalization of what we call action in mechanics. It's not an action in mechanics, because this should be compared not with the mechanics, but with quantum mechanics.
Yes.
And this should be considered as an analog of Schrödinger equation. So, in quantum mechanics, you may write down the wave function of the system. And if you are in the quasi-classical limit, then it starts with the action, but it also has H-bar corrections. So by the way, this was what inspired Feynman to write down functional integral. So the formula for H tending to 0, not as a series, but the value of S at H, where H equals to 0, was known to be the action in mechanics. Then Feynman said, let us take integrals, etc. We will come to this integral. But this has to be compared with this action in mechanics. However, with quantum corrections. So this delta BV is like Hamilton-Jacobi. Like Hamilton-Jacobi equations, however corrected by H. So we will see how these equations are coming. But before we say this Hamilton-Jacobi equation, And then in classical mechanics, what we have here in classical operation is metric. Okay? While here, this symbol depends just on Platonian structure, or just depends on omega BV, or actually, if we have not abstract supermanifold, but T star of X, here we have canonical for T star shifted X, omega BV is canonical. And therefore symbol is uniquely defined. So we have analog of this Hamilton-Jacobi equation. We will have classical master equation.
We will see this, yes?
Yes, we'll see it in a second.
But my question mainly was why SH is polyvector.
Okay, it's because polyvectors are functions on T star 1 of X.
Okay.
So once again, X has coordinates xi. T star has coordinates theta I that are odd, or of opposite parity if X is a supermanifold. Then functions of X and theta are f(I1) In of X, theta I1, theta In, sum over n, sum over I. So that's how polyvectors come up as functions. So it's better to call, so this S of H is nothing but polyvector in this particular case. So I would prefer not to go into full generality. I would prefer to consider this model of when this BV manifold is T star of 1 times X.
Thank you, I see.
Very good. Now, it would be nice. Now, before we differentiate, let us see that this thing has nice geometrical meaning. And this and its geometrical meaning is the following. So if we make Fourier transform of this to differential forms, then it will be de Rham. So this equation is nothing but of e to the s of h over h Fourier transform. And this is very natural, because this is about topology. Okay? So the only crazy idea is, look, you want to study closed differential forms. You think that it is about topology. However, if you are clever enough to put dependence on parameter such that Fourier image has this strange form, you will get interesting theory. Okay? Now let us see how it works. So now, after we understand the geometrical interpretation of it and realize that even before writing equation, we know that it corresponds to, if you wish, cohomology of the RAM of the very special form of this form. We can start writing down equations. So since this is the second order operator, the result of this would be delta BV over S 1 over H plus 1 over H squared, and here we will have this. So how do we actually get it? Let us make computation. Delta BV is d over dxi, d over d theta I. And let us apply it to S over H. It is, let us take the first derivative. ds over d theta I, e to the S over H, 1 over H. Okay? Now I take the second derivative. And this second derivative could hit either here or here. So if it hits the first term, it's 1 over H, d over dxi, d over d theta I, S. And this is delta BV. Plus, another case is when this d over dxi hits here. And everything is multiplied by exponent of S over H, this equals to 0. So here we see BV bracket. And the second is of course, Schutten's bracket. So finally, we are coming to equation. So you may call it BV or Schutten, it's the same. Maybe it's better to call it Schutten BV. Okay? So since we are considering formal power series in H, we come to the following equations. So first, let me denote S equal S naught plus H S1 plus H square S2 plus etc. Okay? So S naught is the value of S when H equal to 0. So let us plug it here. We will have a set of equations. So first equation is S naught equals to 0. So this is what is called classical master equation that we discussed right now, with the meaning that this is a homological vector field. Okay? Now let us look at the equation with the first term in H. What does this mean? So you may ask questions. You are very welcome to ask questions. It means
Can you remind? Please, can you remind? Shooting bracket defines like you had written on the desk. Yes, it's just derivative by theta and derivative by x.
yes, yes.
And there is no sum. It is not. It is not like Poisson bracket, but with.
It is actually it is a Lie Poisson bracket. Shooting bracket is or you may say it is Poisson bracket on the tangent space, on the cotangent space.
Yes. But so shouldn't we write derivative by theta, derivative by x plus minus 1 in something? No, I mean, shouldn't it be two
term?
Two term, yes.
No, because we have s here. If we have the same s.
And?
So, and if you have the same s, if you interchange x and theta, you'll get the same term.
Yes. So maybe there should be a 2.
No.
A factor of 2.
Okay, so in this derivation, there is no factor of 2. You mean between bracket, and so how I defined it. But I may define bracket exactly in this way. Okay, so maybe there is a factor of 2, honestly. So you want to say that vector field with, okay. I am not sure about factor of 2. Okay?
Okay. So it depends on how we define shooting bracket with factor of 2 or without. Yes.
Yes, but I prefer to define it like this.
Okay.
Okay, so here we have this equation for S naught. Now it's instructive to study equation for S1. So how can we get the first order term in H? It comes if we have S1 here or S0 here because of this H in front. So we have interesting equation. So maybe up to a factor of 2. Sorry. This equation also has a nice geometrical meaning. So this meaning says, consider delta BV applied to S naught. It's just divergence of polyvector. Then you are asking if it is Q exact. So the question is, if divergence of S naught considered as a polyvector is exact. So this may be true, or it could be not true. However, what is interesting is that this divergence of S naught should definitely be S naught closed. And it actually is, I would say. Note that delta BV of S naught is closed with respect to this vector field. So it's very easy to show it for the case, I'll show it only for the case when S naught corresponds to a vector field, not to polar vector. Okay? Let us see. So let S naught be theta I V I of x. Okay? So what is delta BV of S naught? It's the divergence of the vector field. So it is actually LV of omega naught over omega naught. Sorry, omega top. How can we rewrite it symbolically? We can rewrite it symbolically as LV of log omega top. So symbolically. Okay? However, this V is actually full homological vector field. So would it be not symbolic notation? We will get that log of omega top is what we are looking for. But this notation is symbolic because there is no such thing as a logarithm of the top form. However, locally it's like this. That's why actually we do have closeness of divergence. But if it's really exact, had to be checked. Okay? Then maybe you will ask, do we have nice examples? Simplest examples where this phenomena doesn't happen, where everything ends at the level of S naught. And I can bring you this example. And this is the simplest anomaly. So anomaly. Class of delta BV of S naught in what? In S naught dot cohomology. Okay? So that's what anomaly is. I think I made a mistake. Not in writing. I made a mistake in recording. I have not switched to the high quality mode. By the way, how do you see me?
I see good enough. It's
Okay,
okay, but not great.
so what do you mean okay, but not great?
I can see your symbols.
You
but
can or cannot?
I can.
Okay. So I'm going to switch the video mode. Okay, so now we work for 1 hour. We need to have a 5 minutes break. Okay?
Okay.
Okay. So I'm back. So you may ask questions. On everything that you have here. At least I don't hear you. Артем, if you are talking to me, если вы мне говорите, то я вас... вот так надо. Угу.
Алло.
A lot of questions. So let us discuss questions.
We're just discussing how we get Laplace formula from divergence of polyvector field. So
Okay, so let us repeat it. So, how to get Laplace from divergence? So first you need to know that delta BV is d over dx I d over d theta I. It's not a standard Laplace. It's BV Laplace.
yes.
So please note that for vector fields, it's a divergence. So we write vector field V as Vi of x theta I and apply. This derivative kills theta and we will get dvi over dxi. And that's what people call divergence.
Yes.
The only question was how we have defined delta BV through divergence.
So actually we define delta BV in the following way. So we take Fourier image. So the natural thing, canonical, is the RAM. Psi I d over dxi. Now we take top form. That identify differential forms and and polyvectors. And then, so this identification is exactly the odd Fourier transformation. So D DRAM, okay, is acting on forms. So now let us take a differential form. And let us make this natural Fourier transformation. Sorry. Here I put psi I theta I, upper index, lower index. So canonical construction. And then we try to integrate our psi. However, this depends on omega top. The measure on psi. So when we do this transformation, then d of omega goes to some d Fourier on its image. And this image is a polyvector field. And d Fourier transformed is exactly BV thing, because multiplication by psi I goes into derivative over theta. So it's a property of Fourier transform. Ah, okay. So it's a property of Fourier transform. Now, is it clear?
It is not clear what is df is.
So it is Fourier, okay. So we have an operator acting on function or acting on function.
Yes.
So like compare, like in ordinary life. We have Fourier transform. So we have a function of x, and we go to the function. So how it's written in calculus? Fourier transform. Then d over dx on f goes to p times f of p. That's how we are solving differential equations. And similarly, x times f of x goes to d over dp f of p. So do you understand this?
Yes, it is clear.
Okay. Now I'm doing the same here. Yes, by the way, if there is an operator, not just one derivative, but operator acting on the left, it goes to the operator acting on the right.
Yes, yes.
In particular, what we have here, operator d over dx squared, it will go to p squared, and vice versa. Because there is an inverse Fourier transform. Now, we call this Fourier image of the operator. So we may ask, what is the Fourier image of the RAM?
It is Laplace BV, as I see.
Yes, it's Laplace BV.
But it is only Fourier image on odd coordinates, yes?
Yes. Fourier image, we are doing Fourier image in the fiber.
Okay, now I see. Thank you.
So you may consider this as a definition. And then you may say, okay, it is the RAM, but on polyvectors. So why did we did such a strange thing? Going from nice the RAM to this guy. And the explanation is because we are looking at the very specific formulas for the expression here that are S over A and S of H over H. So it's actually very specific. Now, we are trying to find H corrections. And I somehow told you that H corrections, so you can compute them iteratively. So in particular, S1, So what is S1? It was written here. So I'm coming again to this equation. This we know. We need to find S1. So what is the meaning of S1? Let me tell you what the meaning is. Okay, so let us discuss. What is the meaning of S1? Note that S1 goes to H at H to the first. So in the expression U of S over H, so we can rewrite it like this: e to the S0 over H. And here we have S1 without H. And here we have higher terms, X times S2, etc. So e to the S1 would stand in front of the measure if we are going to do functional integral with it. At the moment, we don't want to do it, but eventually we would. So let us try to consider example. Let S0 be a vector field. So it should be something like this: VI theta I. Okay? So what is the Laplace BV applied to such a test node? It's DI-VI, divergence. Now, what this means? It means that what? It means that we need to study this equation. Okay, I'll write it as divergence. So this is a function. This is a vector field. It's clear that this is also a function on the base, on X. So let us study the meaning of this function. So here, so we may write left hand side L as LV times S1. On the right hand side, we have LV omega top divided by the omega top. Now we start to see something. That this condition means that consider omega top e to the S1. And let us apply LV to it. It would bring us LV omega top e to the S1 plus omega top. We can apply it here, LV of S1 e to the S1. Let us cancel e to the S1. And we will see up to the sign. So if I put here a minus sign, I will have a minus sign here. We will see that omega top times e to the minus S1 is preserved by the vector field V. So S1 is the ability to create from omega top differential form that is preserved by Q, by commutator with S naught, sorry. What I'm saying is not very easy to see. However, it's true. Okay? So you may compute this and go on. Okay. Now I still want to show you an example. A finite dimensional example where cohomology appears. So let us consider X as having coordinates X, X bar, and theta and C. I would like to take it without index. So it's a Abelian example. Then on T shifted by 1x. It has coordinates xi, x bar I, c, theta I, theta bar I bar, and then something called C star. So I'd like to take X even, and I'd like to take C being odd. And I'd like to propose such vector field. So this seems to be like Euler vector field. Okay, maybe I don't need X bar. So this is an Euler vector field. And it's multiplied by C. So this is odd vector field. Let me call it Q, such that Q squares to 0. Now let me compute divergence of S naught. This is easily computed as C times dimension of X. Okay. Then we want to see if such divergence could be as not applied to something. And this is expected to be a function. So we have some function of x, and we apply to it c xi d over dxi.
Sorry, and what was S naught in this example?
This one. Quadratic vector field.
So Q is S naught is equal to Q actually.
So Q is a vector field. So that's yes.
Mhm.
But actually, no, it's not. So this is a vector field on the base. This vector field on the base could be lifted to the
Mhm.
function on the total space. And
Mhm.
from this, we find Q. So again,
Mhm.
let me explain it again. Let us consider this example. So we have CC sum over I, xi d over dxi. So it corresponds to the action S naught equals C xi theta I. Then Laplace BV applied to it. It differentiates here and here. It's just C times the dimension of bosonic part of X. Okay? X part. So it's some number that is definitely non-zero. That is proportional to C. Now let us see what is S naught applied to S1. That is a function of X. Clearly, it is C times what? Times xi ds1 or dxi. However, you cannot find S1 such that it would be a constant, because you need to say that S1 is log of x. So it's no good change of coordinates, because we are not allowing logarithms. So that's how it goes in one-dimensional case. So this value, not this value, the value of Laplacian BV on S1 for the zero is anomaly. Okay? So we actually can find the analog of anomaly here. Now, I'm trying to consider this theory very seriously, and there are reasons for it. In particular, using this Fourier, I will show you the proof of one of the formulas that I like. Maybe not yet, we will come to it. So this is BV integral classical quantum master equations. I still need to explain one last ingredient in the story. You see, so I propose the following. Maybe we will stop here today at that moment, because we naturally came to the long piece. And we have to keep in 2 hours.
No, we can stop, yes, but we can continue.
We would continue. So let me first summarize. So what we did today, we discussed classical and quantum master equations, okay? Their meaning. We stressed on anomaly. You may ask why it is anomaly. Because you don't see how S0 appears in physics. So tomorrow we will study BV integral, and you would see that this S may be considered as effective action in examples. Effective action depends on Planck constant, because there are loops that there are taking part in effective actions, in effective action. So actually, this is the origin of this H. But in order to understand this, I need to explain more about so-called BV integral. Okay? So I think I may stop here, but I'm going to answer your immediate questions.
So why, maybe I missed something, but why in physics we are interested in BV?
So I'm coming to it.
Okay.
At the moment, I said that this BV is such an interesting thing that many equations have the form of classic BV. So, so I don't see the screen. Now I see it. Okay. And tomorrow, when we will study BV integral, you would see the physics. Okay? I promise.
Tomorrow or
next week.
Uh-huh.
So is the time convenient for you?
Yes.
And what about you, Pavel?
And for me too.
Okay, so I'll ask our American friends why they missed today's session. Okay?
Okay.
And by the way, BV is important in so-called Tau theory, but it's another story.
Interesting.
By the way, people are divided into two camps. People who know and like BV and people who refuse BV, to use BV. So the border is the border between the United States and Canada. So people in Canada like BV. But if you cross the border, no, they do not like BV at all. Okay? So now let us finish. Or maybe you have questions.
I have a comment about time. In all the emails, it's written 2 p.m. New York time, but it's actually 12 p.m. So if you see there is
Oh,
a mistake in timing. So I just calculated with respect to
oh
Moscow
my
time,
God.
but
Okay. That's why Americans didn't come. Maybe it's the reason.
it
So
might be.
you see, with this 12 and this 8, so I
In
added,
the email it is 2.
I
Yeah.
added to 2 this 8. So it's actually right. Okay, I see. So I think that we will do it this way. You may leave, okay? And I will have to give another talk.
Okay.
Okay. Just tell them that it's
Because,
over.
because clients had to be satisfied, okay? It couldn't be that somebody logged in and there is no talk. It's impossible. Okay, well, thank you, Olga.
Yeah, you're welcome.
So hopefully they would not come. By the way, Russian time is correct, yes?
Yes.
Mhm.
So how it would be? It is 8 Russian. Okay, 8 p.m. Russia, 2. So I consider this, it's at S20. Okay, yes, miscalculation. Okay. So please keep the record.
Yes.